All right, here's problem 5, which I cut and pasted the picture of this and it ended up looking horrible. So I'm really not sure what happened. But anyway, so you can't see this here. Well, you can't even see that, can you? Let's see. Let me try, tell you what, this would be a good opportunity to use yellow. So this is T3 is the tension in that, T2 is the tension in that, T1 is the tension here. And you probably can't read this. This is M1, M2, M3. That's probably not actually more readable than it was, so I haven't really helped. But you got these strings connecting these things, okay? Connecting these blocks, T1, T2, T3. And they want to know a few things. First, they want to know the total, the acceleration of the system. It's pulled on with some, well, let's see, I'll show you. It's pulled on with some force of T3 equals, in my case, 65.2 newtons, but whatever. And they give you the mass of the blast. You're given T3 and M1, 2, 3. So, given T3, M1, M2, M3, so part A is what's the acceleration of the system? A equals what? Okay, so what I'm going to do, instead of treating each one individually and doing free body diagrams, which you can do, I'm going to do this much more easily. These blocks I'm going to treat as one mass, with a total mass M1 plus M2 plus M3. And we're pulling these. Please tell me there's no frictionless. Yes, frictionless, thank you. Awesome, no friction. So, what are the forces on this thing? Well, this is M1 plus M2 plus M3 times G. And going up, we have the normal force for 1, 2, 3. I'm going to say the normal force for all of them, so it's the total normal force for them. And then to the right, we have T3. T2 and T1 are internal forces within this system. So we don't represent them. We only represent the forces from the outside. Like T3, we're just being pulled on by this hand. So, we're going to do a free body diagram here. Let's do X and Y. Actually, let me change colors. And so there's our free body diagram for 1 plus 2 plus 3. And here's our dot. So normal force 1, 2, 3. I'm going to save space here and just write weight of 1, 2, and 3. And then you have T3. And those are all the forces you have acting. Here's our coordinate axes, which we're supposed to do. And so let's do a sum of forces in the x direction. And that's going to equal the mass of these three things times A. Okay, so sum of force in the x direction, T3. That's all. Equals M1 plus M2 plus M3 times A, which means then, let's go up here, and A equals T3 divided by M1 plus M2 plus M3. And you can send that to Grandma because that is the answer to part A. Okay, but maybe Grandma wants to know what the answer to part B is. Okay, calculate tension T1. Well, now I'm going to be sneaky here, and I'm going to draw a free body diagram for only mass 1. So here's mass 1. It's being pulled on by this tension. And it's got gravity. So here's our mass 1 free body diagram. Oops. There we go. X, Y. There it is. Gravity. M1 times G. Normal force N. And it's being pulled on by T1. Well, let's do a sum of forces in the x direction, and that's going to equal M1 times acceleration. Nick, what's the acceleration of block 1? Well, we just found the whole system is accelerating to the right. Remember, these chords don't stretch, so they're all stretching, they're all moving together. That's why we were able to do this. And that means we can take this A that we found here and apply it to any of these. So, sum of forces in the x direction is M1A, and that is just T1. So T1 equals M1 times A, and this A up here is what we use. So I guess if we really want to, I suppose if we really want to plug this in, we could say T1 equals, and then, T3 times M1 over M1 plus M2 plus M3. But that is our answer for part B. Part C, let's see. Part C is to calculate tension T2. Again, basically the same drawing, except now you can just take M1 plus M2 and say those are being pulled to the right by T2. So now we're just taking these two here, C, drawing a box around them. You got T2. You're going to have normal force on 1 and 2. You're going to have the weight of 1 and 2. I'm not going to write mg because we discovered in these frictionless problems we don't need it. So FED of 1 plus 2, we have normal force on 1 and 2. We have the weight of 1 and 2, and you have tension in rope 2. And so what we get then is tension in rope 2 is M1 plus M1 plus M2 times A. And so this is basically going to be very much like what we got up here, except slightly different. T3 times M1 plus M2 over M1 plus M2 plus M3. So there you go. So what the way you can take away from this system is if you're looking at the tension in these ropes, and you're pulling on one, and there's a whole string of these things connected, and you could add more. What you'd see is the tension is highest in the one you're pulling on, and then each one back has less and less tension, because what you're doing here, this tension is enough to pull the entire thing along. This tension is only enough to pull these two. This tension is only enough to pull these, or sorry, pull this one. So the further down you go in your thing, the less the less tension there is. And you can think about that if you can imagine you had a bunch of these things, there's a bunch of, like, I don't know, blocks linked by strings, and you're pulling on in sort of a chain like this, and you're pulling on the one at one end, then if one of the strings is going to break, you expect it to be like the one you're pulling on, or one of the ones up near the front, because those have the most tension. The ones near the end aren't going to break. So anyway, that's problem 5.